Well, there's another kind of important notion we have is if we have a vector, what are things that are perpendicular to that vector? If we want everything perpendicular to it, what do we get? So let's say we have a vector here. I'm going to draw it pointing straight up. Well, something perpendicular to it might look like, but since we're in three-dimensional space, we have another direction to be perpendicular in, say this way. Right? So we have kind of a whole two-dimensional space of perpendicular things. Right? And this is called a plane. So what this really looks like, say we extend this all out, and then we'll see something that looks like this. So you have this blue vector, which let's get in the habit of calling this perpendicular vector n. And then we have the plane that it's perpendicular to, right? So that's the other, I've drawn over myself. So that's the other thing we can do. We can start with the vector and take everything perpendicular to it. So how do we start trying to figure out an equation for this? Right, the equation for the line, we started with some point on the line. So let's do a similar thing here. Point. All right? But now, there's not really one direction to specify for the plane anymore. There's a combination of two. So how do we come up with an equation now? Well, we can think of that plane as consisting of a whole bunch of vectors, all of which are perpendicular to n. So think of it like this. If v is a vector in, let's give this plane a name. Let's call it capital pi. So if v is a vector in pi, in the plane, how does it relate to n? Well, how do you check if two vectors are perpendicular? 2 sections ago, you should have seen something called the dot product. And we know that n is perpendicular to v if n dot product v is 0. Right? So that's how we can check if two vectors are perpendicular. Okay. So we're starting to get somewhere. But how do we describe v? Right? I mean, we can't just say, here's some vector in the plane. We need some actual coordinates for it. Well, displacement vectors are going to come and save the day again. So let's say we have P, our point in the plane, and we pick some other point in the plane. Let's call it Q. Right? Then we can form the displacement vector, and this is what we'll call V. All right, so let's say this point P is some prescribed point. Sorry, not P here. P equals x naught, y naught, z naught, right? And then Q, remember I want Q to be very generic. So Q is actually just going to be x, y, z. And what x, y, and z can be will be restricted by this equation over here. So the vector v, which is the displacement vector, pq, this is given by, let's move over here, x minus x naught, y minus y naught, z minus z naught. Right? So we're going to combine that together with this equation. And of course, I guess now we need to give n some coordinates, or some components. So let's call it ABC. So we now have our two vectors that have to be perpendicular to each other. So this equation looks like A, B, C, dot product with x minus x naught, y minus y naught, z minus z naught, and this has to be 0. And I keep writing over myself. Okay, this is a good spot. All right, so we have this equation here. That's really a pretty decent equation of a plane already. But we can do the dot product and get something that doesn't involve vectors and dot products, something that's just a regular equation. Right? So if we write out this dot product, this gives us A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught, equals 0. Right? So that's another equation for the plane. And notice it's given in terms of this vector n in front, and then the x, y, and z just have the point P subtracted from them, or the coordinates of the point P subtracted from them. All right. So what we need to do now is actually give this vector n here, this perpendicular vector, a name. And its name, this is the normal vector. So normal is another word for perpendicular. I'm sorry to say Calc 3 is going to kind of overuse the word normal. It's going to show up, I think, 2 or 3 more times. So hopefully we can keep that all straight. But usually it'll be called n. There's a benefit. All right. So one more thing we can do here with this equation is actually combine it down to a very simple thing. All right, so we can combine this all to ax plus by plus cz equals d. Right? And that's just by multiplying everything out. So of course d here is going to end up being ax naught plus by naught plus c. So one thing please don't get confused on, remember when we're back in the xy plane, graphing something that looked like this, but covering this doesn't really work so well. But without this guy, so just ax plus by equals d, that would be a line. Right? But in 3-dimensional space, if we have an equation that looks just like this, ax plus by plus cz equals d, this is now a whole plane. Right? And that's a consequence of adding on that extra direction.